Hello students, myself Santosh Jagtap from HM College Kannada. Today we are going to discuss vibration magnetometer. Okay, first of all we discuss about some basic concepts regarding with magnetometer. Okay, as you know that if any bar magnet is kept in uniform magnetic field, it experiences the torque. And the formula of the torque is tau bar is equal to m bar cross b bar. Okay, here is cross product. Then we know that here we can write here m into b into sine theta. Okay, where m is magnetic dipole moment and b magnetic induction in which this bar magnet is kept. Okay, now what is about the vibration magnetometer. Vibration magnetometer is an instrument used to compare the horizontal magnetic field of Earth at two different places. Okay. Also, it is used to compare the magnetic dipole moment of two bar magnets. Okay. It consists a simple box. Okay, and the base of the box and the mirror is adjusted at the base of the box, and a bar magnet is placed on that mirror, which bar magnet is pivoted at the center. Okay, and this is the Earth's horizontal magnetic field BH. Okay, if we displace that bar magnet with small angular displacement, then restoring torque is developed in that bar magnet. Therefore, by the formula we can write here torque is equal to m into b into sine theta. Okay, due to the restoring torque we can write here minus, that is torque minus torque is equal to minus m b sine theta. Okay, now if angular displacement is very small, then instead of sine theta I can write here only theta. Therefore our formula becomes torque tau is equal to minus m into b into theta. Okay, but we know that torque is equal to I into alpha. I means moment of inertia and alpha means angular acceleration. Then I can write here torque instead of torque in this equation. I can write here I alpha is equal to minus m into b into theta. Okay, alpha means angular acceleration. Then we know that alpha is equal to d2 theta by dt square. Okay, then I into d2 theta by dt square is equal to minus m into b into theta. Okay, now d2 theta by dt square is equal to minus m into b divided by I into theta. Okay, comparing this equation with linear simple harmonic motion. Okay, and we know that differential equation of linear simple harmonic motion is d2x by dt square is equal to minus omega square into x. Okay, then comparing these two equations, here is angular displacement, here is linear displacement. Okay, for that purpose omega square is equal to mv divided by I. Okay, then I can write here, comparing these two equations, I can write here omega square is equal to mv divided by I. Okay, that is omega is equal to square root of mv divided by I. Okay, and basically we know that the time period t is equal to 2 pi divided by omega. That is t is equal to 2 pi divided by under root mv divided by I. Okay, that is t is equal to 2 pi under root I divided by mb. This is the formula of the time period of vibration magnetometer. Okay, where t is time period, 2 pi is constant, I moment of inertia of a bar magnet, m magnetic dipole moment of a bar magnet, b be the external magnetic field in which that bar magnet is kept. Okay, right. Now we are going to discuss some basic points regarding the dipole. Okay, consider this is the bar magnet. Here is north pole, here is south pole, and distance between poles are called as a dipole length. Okay, and we know that the pole strength of the north pole is plus qm and pole strength of the south pole is minus qm. Okay, then magnetic dipole moment m is equal to, formula of the magnetic dipole moment is m bar is equal to qm into 2l bar. Okay, then finally I can write here m bar is equal to qm into 2l bar. Okay, now if we cut that magnet along the perpendicular of its length, that is, this is the length of the bar magnet, and we cut this bar magnet perpendicularly. Okay, then we can write here, this is the small segment of the bar magnet, here is south pole, and the newly formed here is north pole. Okay, the pole strength is remains same, that is, this length, this south pole have minus qm and north pole have plus qm pole strength. Okay, then magnetic dipole moment m bar dash, okay, is equal to qm multiplied by this length becomes half, that is l. Okay, then we can write here is equal to qm multiplied by twice l divided by 2, but qm multiplied by twice l, qm multiplied by twice l, this is nothing but m bar. Then finally we can write here m bar dash is equal to m bar divided by 2. Okay, it implies that when we cut the magnet at the center perpendicular to the length, the pole strength remains same, but its length divides into the two equal parts. Okay, for that purpose the dipole moment becomes m divided by 2. Okay, now next, if we divide that magnet along its length, that is, it becomes like that. Consider this is the original bar magnet. Okay, here is south pole, here is north pole, and we divide this bar magnet into the two equal parts along its length, that is, we cut from here. Okay, then pole strength is divided into the two groups, but magnetic length remains same, that is, the newly formed bar magnet having pole strength minus qm divided by 2 and plus qm divided by 2. Okay, and this is the another bar magnet. Okay, this is plus qm divided by 2 and this is minus qm divided by 2. Okay, and instead of that, all the dipole length remains unchanged, that is, distance from that point to distance from that point is 2l. Now, what about the magnetic dipole moment? Then m bar is equal to qm divided by 2. qm divided by 2 multiplied by twice l. Okay, and qm into twice l, qm into twice l, it becomes m. That is, we can write here m double dash, I can write here double dash, m bar double dash is equal to m bar divided by. Okay, the summary of that divide the bar magnet into the two equal parts, perpendicular to the length or along the length. Its dipole moment becomes half. Okay, its dipole moment becomes half. Right on. Now the next point is, if we put a two bar magnet one over the other, that is, this is the one bar magnet. Okay, here is south pole and here is north pole, and another bar magnet. Here is the north pole and here is south pole. The magnetic dipole moment of first magnet is M1 and magnetic dipole moment of the second magnet is M2. Then resultant magnetic dipole moment of that combination is M bar is equal to M1 bar plus M2 bar. Okay, this is the first case. Now about the second case, if the pole of that magnet are opposite to each other, that is, we can write here, if this is the south pole and this is the north pole, magnetic dipole moment is M1 and another magnetic dipole moment of south pole is here and north pole is here. In this case, both poles are in the same direction. In this case, both poles are in the opposite direction. Then the magnetic dipole moment of the first is M1, magnetic dipole moment of the second is M2, but these two are the oppositely directed. Then we can write here M bar is equal. Okay. Here we clear that point. That is, if M1 bar is greater than M2 bar. I repeat, if M1 bar is greater than M2 bar, then we can write here M bar is equal to M1 bar minus M2. Okay, M1 bar minus M2 bar, because both are oppositely directed here, both are in same direction. Okay, now if here is an angle, that is, consider here is south pole and here is north pole. Okay, another bar magnet of here is south pole and here is north pole. Then direction of the magnetic field, direction of the magnetic dipole moment is M1 bar and here is M2 bar. Then theta is the angle between that two. Okay. Then M bar is equal to, in bracket, in square root, M1 square plus M2 square. Okay. Plus or minus. Okay. Depending upon that angle. Okay. I can write here plus or minus 2 M1 M2 cos theta. Okay, plus or minus here sign because depending upon that angle. Plus or minus 2 M1 M2 cos theta. Okay, now the next point. If angle between that two is 90 degree, okay, that is, arrangement of the two bar magnet is like this. Or arrangement of the bar magnet is like this. Like this. Due to that arrangement, angle between M1 and M2 is 90 degree. Due to that arrangement, angle between M1 and M2 is 90 degree. Cos 90, 0. Okay. Then we can write here resultant magnetic dipole moment M bar is equal to under root of M1 square plus M2 square. Okay, these are the resultant magnetic dipole moment at different positions of two bar magnet. Now we are going to discuss some problems regarding with magnetometer. The first problem is that the magnetic moment of two identical magnets are M and twice M. Both are combined in a such way that similar poles at same side. Okay, that is, its combination becomes like that. म्हणजे दोघांचे जे पोल्स आहेत ते सेम डायरेक्शनला असतात. हा पहिला आणि हा दुसरा असेल. ओके, असं ज्या वेळेला असेल त्यावेळेला आपल्याला तो या ठिकाणी साऊथ आहे, या ठिकाणी साऊथ आहे, इथं नॉर्थ आहे, इथं नॉर्थ आहे. त्यावेळेला मात्र आपल्याला जे मिळणार आहे मॅग्नेटिक डायपोल मोमेंट आहे तो दोघांचे समेशन असणार आहे म्हणजे m बार किंवा आपण असं म्हणूया की m1 म्हणूया. m1 बार इज इक्वल टू पहिल्याचे m दुसऱ्याचे ट्वाइस म्हणजे m plus twice m, it becomes 3m. Okay, this is the first arrangement. And now the second arrangement, at that time the time period is t1. Okay, it implies that the time period is t1. Now about the second arrangement, if polarity of the one magnet is reversed, that is, now in second condition here is south pole and here is north pole, here is south pole, here is north. Okay, then the time period becomes t2, that is m2 bar is equal to 2m minus m is equal to m. Okay, and at that time period is t2. Okay, now we know that the time period of the magnet kept in uniform magnetic field T is equal to 2 pi under root I divided by m into p. Okay, therefore here is t1. Okay, here is t1 2 pi I divided by m1. At the same place the polarity of the poles of that two bar magnet are reversed at the same place. For that purpose b is constant. Okay, and there is no effect on the moment of inertia, that is I becomes constant. Okay, then we can write here t2 is equal to 2 pi under root I divided by m. Instead of m1 we can write here m2 into p. Okay, and taking the division of that two equations, okay, I can write here t1 divided by t2 is equal to, finally we can write here 2 pi gets cancelled, I gets cancelled, b gets cancelled. Okay, I can write here t1 divided by t2 is equal to square root of m2 divided by m1. Okay, t1 divided by t2 is equal to square root of m2. m2 means m. Here is m and here is m1 means 2 plus 1 3. It is 3m. m gets cancelled. We can write here. It implies that t1 divided by t2 is equal to under root of 1 by 3. This is our answer. Okay, right on. Now in the next problem, a magnet is suspended in a such way when it makes a 20 oscillation per minute where deep angle is 30 degree. It implies that whenever the bar magnet is kept in a place in a uniform field at which deep angle is 30 degree, that is, we can write here theta 1 is equal to 30 degree. Okay, and at that time it makes, that is the frequency is given, it makes 20 oscillations per minute. Then we can write here F1 is equal to 20 divided by 60, converting that into the second. Okay, simplifying that, it becomes 1 by 0. Okay, and now next is, it makes up 50 oscillations per minute where dip angle is 60 degree. It means that when that magnetometer or the magnet is kept in the second place where the dip angle is 60 degree, that is, we can write here theta 2 is equal to 60 degree. Okay, it implies at that particular time frequency, at that particular place frequency is 50 oscillations per minute. Then we can write here 15 divided by 60, that is 1 by 4. Okay, find the ratio of the Earth's magnetic field at two places, and in bracket the magnet placed in a horizontal magnetic field of Earth. That is, okay, finally we can write here the time period T is equal to, we know that T is equal to 2 pi under root of I divided by MB. Okay, and this magnet placed in horizontal magnetic field of Earth, therefore B we can write here, instead of B we can write here BH, because this bar magnet is kept in uniform magnetic field of Earth and direction is horizontal. Okay, therefore we can write here T1. T is equal to 2 pi under root I divided by MBH. Okay, we know that the relation between frequency and time period, we can write here 1 upon F is equal to 2 pi under root I divided by MBH. Okay, and if there are two cases, then we can write here 1 upon F1 is equal to 2 pi I, because bar magnet is same, therefore I becomes same. M means magnetic dipole moment of the bar magnet. The bar magnet is same, therefore M is also same. Okay, and here BH. Okay, and here we can write here B cos theta, and for first case here is theta 1. Similarly, we can write here theta, 1 upon F2 is equal to 2 pi under root of I divided by M B cos theta 2. Okay, this is equation number first and this is equation number second. Now, dividing both equations, we can write here, dividing both equations, we can write here, okay, 1 upon F1 divided by 1 upon F2 is equal to 1 upon F1 divided by 1 upon F2 is equal to 2 pi under root of I divided by MB1 cos theta 1 divided by 2 pi under root of I divided by MB2 cos theta. Okay, 2 pi gets cancelled. I gets cancelled. M gets cancelled. Okay, we can write here F2 divided by F1 is equal to F2 divided by F1 is equal to under root of, okay, F2 becomes upward and F1 downward. And 2 pi gets cancelled, I gets cancelled, and B gets cancelled. Okay, B2 cos theta 2 divided by B1 cos theta 1. It is 1. Okay, squaring on both sides, we can write here F2 square divided by F1 square is equal to B2 cos theta 2 divided by B1 cos theta 1. Okay, now putting the value of the theta 1 and theta 2, we can write here is equal to B2 divided by B1 multiplied by cos theta 2, that is cos 60. Cos 60 divided by cos theta 1, that is 30. Here you can write here cos 30. Okay. Then B2 divided by B1 is equal to F2 square. F2 1 by 4. F2 square, that is 1 by 4. Then I can write here 1 by 4 multiplied by 1 by 4 divided by 1 by 3 multiplied by 1 by 3. Okay, multiplied by cos 60. 1 by 2 divided by cos 30. Root 3 by 2. Okay, 2 gets cancelled, and simplifying that equation, I can write here B2 divided by B1 is equal to, becomes of order 9 divided by 16 and root 3 goes over, then we can write here root 3 multiplied by 9. Okay, then finally we can write here B1 divided by B2. B1 divided by B2 is equal to 16 divided by 9 into root 3. This is our answer. Right. Now the next problem. The time period of the thin rectangular bar magnet of vibration magnetometer is T. If it is broken into the two equal parts, find time period of each part at same place. Okay, along its length, perpendicular to its length. Okay, first of all we are going to discuss the broken cases of that bar magnet. Consider this is the bar magnet of moment of inertia I, and moment of inertia of a thin rectangular plate is ml square divided by 12. Okay, and formula of the magnetic dipole moment is m is equal to qm multiplied by twice L. Okay, twice L, it means that the magnetic length. Okay, for simplicity we can write here only L. Now if the length between that two poles is L. Now first case, if the bar magnet is broken along its length, okay, and second case is perpendicular to its length. Along its length means the bar magnet is broken at that condition. Okay, that is there are two parts. This is the first part and this is the second part. Okay, this is the first part and this is the second part. Okay, now about the I, moment of inertia of that part is I, and moment of inertia about that each part, this is the I1. Okay, the axis of the vibration is perpendicular axis, axis of the vibration is perpendicular axis. Okay, the distance remains same, but mass is divided into the two groups. Okay, therefore I dash is equal to m divided by 2 multiplied by L square divided by 12. Okay, for simplicity we can also write here for simple manner m1 into L square divided by 12. Okay, m1 with the mass of each part. Okay, and m1 is half of m because the bar magnet is broken into the two equal parts. Therefore I1 is equal to m divided by 2 L square divided by 12. But ml square divided by 12, ml square divided by 12 is original moment of inertia. For that purpose I can write here I1 is equal to I divided by 2. Okay, and we have already studied that when the bar magnet is broken along its length, then M1 is equal to capital M divided by 2. Okay, the time period of that part is, we know that T is equal to 2 pi under root I divided by M into B. Okay, B remains same. I repeat, okay, B remains same. Therefore, T1 is equal to 2 pi under root I1 divided by M1 B. Okay, that is simplifying that T1 is equal to 2 pi under root I1. I1 means I divided by 2. Here I can write here I divided by 2 whole divided by M1B. M1B, that is M divided by 2 into B. 2 gets cancelled. We can write here T1 is equal to 2 pi under root I divided by M into B. That is, there is no difference the time period of the original bar magnet and bar magnet is broken into the two equal parts along its length. Okay, that is T1 is equal to T. This is the first case. Okay, now about the second case. About the second case, if bar magnet is broken perpendicular to its length, that is, we can write here the bar magnet is broken along the perpendicular to its length. Okay, then this length becomes L by 2. Okay, and mass becomes M divided by 2. Then moment of inertia I is equal to original moment of inertia I is equal to ml square divided by 12. Okay, now newly formed pieces having moment of inertia I2 is equal to m2. Okay, L2 square divided by 12. Then M2 means M divided by 2. M divided by 2 multiplied by L2. L2 means L divided by 2 and square. Then we can write here L square divided by 4 multiplied by 1 upon 12. Okay, 4 into 2, 8. We can write here ML square divided by 12 multiplied by 1 by 8. That is ML square divided by 12. ML square divided by 12. It becomes I. We can write here I2 is equal to I divided by 8. Okay, and dipole moment M is equal to M divided by 2. We have already studied that. Now the new time period T2 is equal to 2 pi under root of I2 divided by M2 into B. Okay, that is T2 is equal to 2 pi under root of I2. I2 is I divided by 8. I can write here I divided by 8 divided by M2. Okay, this is the M2. M2 is M divided by 2. Here we can write here M divided by 2 into B. Okay, 2 pi says 1, 4. Then I can write here T2 is equal to 2 pi under root I divided by 4 divided by MB. Okay, taking the 4 outside of the square root, we can write here T2 is equal to 2 pi divided by 2 under root of I divided by MB, and 2 pi under root I divided by MB. This is original time period. Then we can write here T2 is equal to T divided by 2. I hope you understand all the concepts regarding with the vibration magnetometer and problems regarding with that point. Thanks for watching this video. Thank you.